Welcome back, Physics 30. So if we kind of look, we did these examples here, and I kind of looked at this rationale. Maybe we should do that with all of them here. So if we look at badminton racket and birdie, I think a badminton racket is more heavy than a birdie. So let's look at, so again, we're looking at F net equals ma, Newton's second law, but rearranging that to solve for A. So A equals F net over m, and A is equal to F net over m. So if you look at birdie, and this mass will be racket, because that's what the force is being exerted on. So we have the same forces involved here. So the racket pushes forward on the birdie pushes back on the racket. They're identical. But if we compare the masses, a birdie's mass is much less than a racket. So the acceleration experienced by the birdie will be quite large as the racket is hitting it. And the acceleration that a racket would feel, since it's so much bigger than a birdie, would be relatively small. All right? And we could do that for here too. Figure out the masses there. But it really stands out if we have two separate objects like that. Two separate objects. The bullet here is really, really tiny. The gun is really, really large compared to the bullet. So we still feel the kickback of the gun, but that acceleration that the gun experiences as it's shooting the bullet is far less than what the bullet feels. All right, so we look at the last two examples here. This one's kind of interesting. An apple falling to the ground. So we have an apple as one object. The big question is, what is the second object? What is applying a force on the apple? Well, of course, we know it's gravity. And what is making the gravitational force? The Earth. So we could think of this. Earth applies a downward force on the apple. And if I interchange those objects, the apple applies, and I'll change the direction of this, upward force. And then these two objects were changed. The Earth. Now this is weird. An apple is pulling up on the Earth? And in fact it is. It is. But if we relate it to this to see, well, how much is my acceleration going to be for each of these? Here's where it comes together and it makes sense. So on this first one, their force is being exerted on an apple. And here the force is being exerted on the Earth. So over here on the apple is a really small object. So if these two forces are equal, the apple is going to experience acceleration. And we can see it speeding up as it's coming towards the ground. Now, we don't see the Earth accelerating upwards towards the apple because the Earth is way massive. So if we have a number here, which is equivalent to up here, divided by a humongous number, we get something that's infinitesimal, extremely small. So small you can't even register it. So it works. Just because we have equal forces doesn't mean things are going to move. It's dependent upon the mass here as well, from Newton's second law. Okay? So the acceleration will be high if it's a small mass, and it'll be really, really small if it's a large mass. All right, one more example. Pushing against a wall while wearing roller skates. So we kind of touched on that with that picture of that lady pushing on the wall with ice skates. So person applies a forward force on the wall, and interchange those two. The wall applies I'll make this the opposite, backward force on the person. So again, you're pushing against the wall, and the wall isn't going to move because it's attached to the ground. But the force that we want to get out of pushing against the wall is the reaction. The harder we push forward, the harder the wall pushes backwards on us. So if we could just give a little nudge, we get a nudge back. But if we push really, really, really hard, the wall is pushing back on us really, really hard. And you can feel that. You can feel when you press against a wall, you feel it pushing back. If you're sitting down right now, you feel the chair pushing up on you. I think you do. So the earth is pulling you down, and then there's an equal and opposite force there with the chair pushing up on you. So it's almost like you're applying a forward force on the chair because the earth is pulling you down, and the chair applies an equal and opposite force on you. So you feel this on your buttocks. You feel it on your feet if the ground is touching you. You're pushing down on the ground, and the ground is pushing back up on you. So all of these paired up forces occur all the time, and they're equal and opposite. Downward force, upward force, forward force, backward force. All right? So you should be able to do the assignment. The assignment's fairly easy, just kind of defining or determining what the action-reaction forces are. So you should be able to do well. All right, we'll see you again.